So the next paper we read was Convolutional Networks for Images, Speech, and Time Series. And this paper talked about why convolutional networks, or CNNs, are better candidates than regular feed-forward networks. This is because of backpropagation and the fact that CNNs integrate shared weights, so each filter is replicated across entire visual field and forms a feature map. So a convolutional network is a network in which each layer has multiple feature maps. So for the structures of convolutional networks, which is discussed in this paper, there is an input layer which receives size-normalized images. There's a convolutional layer or multiple convolutional layers, and these are often alternated with pooling layers which perform downsampling. So once a feature has been detected in an image, its exact location is less important as long as its position in relation to the other features is known. So the convolutional layers reduce the resolution and pass it on to the next layer until it eventually gets to the output layer. So a very simple implementation of this is shown here. So this is with the CIFAR 10 dataset, which is just a dataset with 10 classes, and each class has 6,000 images. This function is just loading and transforming the data to be used in the code. And this function just shows some random training examples like car, plane, ship, and bird. And the next one defines the net class. So in the initialization of the net class, there is a first convolutional layer, and there's 3 inputs, 6 outputs, and a kernel size of 5. There's a pooling layer, and there is another 2-dimensional convolutional layer. There are also linear layers in the initialization, and there is also a forward function. The back function doesn't need to be defined. And the forward function includes a ReLU function, which is an activation function. So the criterion is defined for cross-entropy loss. Optimizer is just the default that you can find on the PyTorch website. So for training the network, we trained it for 2 epochs. So we would loop over the data iterator. We get the inputs and label from the data that we loaded earlier on. And then this is fed into the network and then optimized. So you can see here that it prints out every 2,000 batches, and it prints out what the loss is when it's done training. So after we trained the network, we ran it on some testing data. And so you can see that it prints out the accuracy of the network on 10,000 test images. So you can see here that the pictures are cat, ship, and plane, but the prediction of the network is ship for all of them, which is why the accuracy of the ship is 97%. The accuracy of the rest of these are not as high, especially because this was only trained for 2 epochs. So the next paper we read was on deep neural networks, and deep neural networks is a more umbrella term that encompasses CNNs. So in this paper, the authors explain the concept of fooling images, which are images that can't really be classified because they're unrecognizable to the human eye, but deep neural networks classify them as familiar objects with more than 99.6% certainty. So the authors explain how they worked with the MNIST dataset and ImageNet images to try to trick the neural nets into classifying fooling images. So this paper is kind of an extension of CNNs. It is focusing more on the idea of overfitting. So this paper is just supposed to highlight the difference between how deep neural nets and humans recognize images and objects.
So this is the IPython notebook for our reinforcement learning example. We're doing that through finding the shortest path from 0 to 9. And so this array kind of shows us all the linkages between the individual points marked with these numbers. And then this part is just more initialization. This just shows us in a matrix form what are possible moves. And this cell is kind of training our policy network, which is marked with the Q. This update function kind of tells us, or it updates the policy network so that it adds on a given score. And so by the very end, after we train it, the policy network will have one move with a higher score than the rest, and that's the move that our program chooses. And so at the very end here, you see we have the training portion, which is kind of training that policy network so that our program can select the right options. And we have it printed right here. And then this last part is testing it. So we just run the policy network and see if it actually works and if it actually finds us the quickest path. And it does.